Welcome to the AI Research Roundup. I'm Alex. Today we're looking at a paper from the Hugging Face trending list, published on March 2nd, 2026, just yesterday. It introduces a new framework called OmniLottie that achieves a massive 97% success rate in generating vector animations from text, solving the structural issues that caused previous models to fail completely. The paper is titled OmniLottie, Generating Vector Animations via Parameterized Lottie Tokens. And as we'll see later, the implications for automating complex graphic design workflows are really promising. And for those interested in the implementation, the authors have shared their code on GitHub. Figure 1 illustrates the broad capabilities of OmniLottie in generating vector content. On the left, a large grid of samples demonstrates the variety of outputs, ranging from simple UI icons like folders and checkmarks to dynamic character animations like bouncing emojis. On the right, the diagram details the 3 specific generation tasks the model supports. First, text-to-Lottie creates animations from scratch using just a description. Second, text-image-to-Lottie takes a static image and animates it based on a prompt. And finally, video-to-Lottie converts raw video footage into clean, scalable vector graphics. Well, having seen the model's capabilities, Figure 2 details the pipeline used to construct the underlying dataset, OmniLottie2M. On the left, the process begins by collecting raw data from 2 sources, converting static SVG datasets into animated Lotties, and gathering professional files from online repositories while filtering out low-quality assets like embedded raster images. The middle column shows the data processing stage, where these animations undergo spatial temporal normalization and are rendered into video frames to help the model understand motion. Finally, on the right, the data annotation block pairs these visuals with multi-level text descriptions, ranging from short captions to detailed paragraphs about geometry and motion, which creates the rich supervision needed for training. So Figure 3 introduces the OmniLottie framework itself. The left panel illustrates the core challenge. Raw Lottie files are complex JSON structures filled with nested layer attributes and metadata. To address this, the middle panel shows the parameterization process, where the model flattens that hierarchy into a simplified sequence of command tokens. Finally, the right panel depicts the full pipeline, where the QN 2.5 VL backbone takes multimodal prompts and autoregressively predicts these tokens to render the final animation. Alright, Table 1 presents the quantitative results, comparing OmniLottie against baselines like GPT-5 and specialized tools across real and synthetic subsets. Looking at the real subset, the success rates tell a clear story. While general models like QN 2.5 often fail completely with 0% success, OmniLottie consistently achieves around 90%. It also proves much more efficient. In the text-image task, for instance, it generates animations in about 89 seconds, whereas optimization methods like AniClipArt take over 1200 seconds. Finally, the lower F versus D scores and high motion alignment numbers confirm that the output isn't just valid, but also visually superior. So while Table 1 proved the efficiency, Figure 4 provides a visual comparison for the text-to-Lottie task. The top rows display the input prompts, such as requesting a stylized monitor icon. In the middle rows, we see that general-purpose models like GPT and DeepSeek are dominated by red failure icons, indicating they could not generate valid file structures. However, the bottom row shows that OmniLottie successfully renders the requested graphics with correct motion and geometry. Okay, effectively, Figure 9 explains the efficiency that makes this performance possible. On the left, the bar chart identifies the problem, where the raw JSON format shown at the bottom spans over 2,500 tokens. The pipeline on the right illustrates the solution. It progressively compresses this data, transforming raw code into text sequences and finally into quantized tokens. This achieves an 81% reduction in size, shrinking the sequence to just 486 tokens, which drastically simplifies the generation task. Wrapping up, 2 main takeaways stand out. By replacing verbose code with compact parameterized tokens, OmniLottie effectively solves the structural hallucination problem that held back previous models. Furthermore, the release of the OmniLottie2M dataset establishes a robust foundation for future vector animation research. Together, these contributions could significantly lower the barrier for creating professional, editable motion graphics. That's it for this episode of the AI Research Roundup. I'm Alex. Thanks for listening.